In section 1.3, we're going to look at differential equations as mathematical models. In this section, we introduce the notion of a differential equation as a mathematical model and discuss some specific models from biology, chemistry, and physics. Okay. So one of the things that we're going to talk about is that the mathematical description of a system or a phenomenon is what we refer to as mathematical modeling. It's an attempt to write down equations that model the real-world phenomena that typically we see. Okay. For example, one of the things that someone might be interested in is the way in which population dynamics of animals grow. So how do species populations evolve over time? Certain things that are important there is obviously the birth rate, the number of births that's possible during a birthing session, as well as the death rate. If you have any kind of predator-prey kind of relationships where they themselves need a food source, or they might be the food source for some other population, that all kind of comes into play with how much of that animal exists at a particular point in time. Generally speaking, whenever we want to start the construction of a mathematical model or system, the first thing that people would want to do is identify the variables that are responsible for changing the system. Okay, so in particular, you want to identify, okay, this is the thing we're trying to model. What things impact and go into changing this system? At a very basic level, and especially in our class, we're going to look at some of the more simplified versions. So we might not want to incorporate all of these variables into the model at first. You might want to choose simply just one or two that would have the overall biggest impact while ignoring the rest. And in this step, what we are doing is we're specifying the level of resolution for the model. There's kind of this fine balance and trade-off that typically kind of goes into play, and that's that, when you have a model that has a high resolution and a high level of variables in it, yes, it becomes more accurate, but the downside is because of that added complexity and all those other dimensions, it can oftentimes make finding solutions extremely difficult. On the other end, if we take a model that has a low level of resolution, then we're kind of cutting out a lot of the extra stuff and focusing on maybe one or two key aspects of things that change the model. The trade-off there is that with this simplified version, we might be able to find explicit solutions and solve it more easily, but at the same time, the simplified model might not actually give us the best approximation of what's really going on. So there's kind of this trade-off. You don't want to have too low resolution in general. Too high resolution can be very difficult to work with. So it's kind of like this Goldilocks zone where it's really kind of a struggle. The second thing is that we want to make a set of reasonable assumptions or hypotheses about the system we are trying to describe. These assumptions will also include any empirical laws that may be applicable to the system. Okay. As it pertains to our class, we're going to be very specific with the types of models that we're going to use. We will look at a few classical ones. We'll definitely look at population dynamics and growth. We'll look at radioactive decay. Things that can model the spread of infectious disease. I might throw in a couple of the Newton's laws of warming or cooling, and then mixture problems is also a classical type model that's done in a course like this. So we'll hit all of those kind of high points. And the goal throughout the rest of this section together is to kind of, inform you on some of the assumptions we're going to be making and how those will lead to the models that we are going to be using for our class. Okay, as another example, I'm sure most of you have probably at this point had a physics class. In undergraduate physics, especially the first couple of classes, if you look at, for example, say projectile motion, we heavily focus on the effects of gravity on projectiles, but oftentimes they would just kind of ignore, in the very beginning, the impact of air friction because it kind of makes the model more difficult to deal with. Similarly, if you're talking about projectile motion in terms of like rockets and things that are going through inner space, then where things are launched at makes a big difference. And so even more higher resolution model might want to include things such as the curvature of the Earth. Okay. So there's kind of like this steps in modeling with differential equations, kind of a flow chart, if you will. So the first thing we would want to do is these are the assumptions and hypotheses that we are going to work with. So these are the things we're going to focus on. These are going to kind of dictate the level of resolution that we're going to have for our models. We express the assumptions in terms of differential equations, so we actually formulate them. We write down the equations that we get based upon our assumptions and hypotheses. We, to the best of our ability, with methods that we will learn in this class, will solve those differential equations to obtain solutions. And then what we would like to do is ask the question, well, how reasonable are those solutions do we get? Do they accurately predict the things that we're able to observe? So we want to kind of see how well our model did with doing some basic predictions. And then from there, once we've kind of checked to see how accurate our model is, then we might want to go back and tweak it, maybe raise the resolution a little bit, or perhaps keep the level of resolution the same, and focus on maybe some of the other underlying variables or things that could impact our dynamic. So hopefully everybody's familiar with the idea of something being proportional. A lot of times we'll say that, A get my whiteboard up. So a lot of times we would say that A, if I can draw, just give me 1 second. There we go. So we would say that A is, we use a symbol for proportionality. Proportional to B means that 1 is just a constant multiple of the other. We could say that A is proportional to the square of B, in which case we could write A as some constant times B squared. A lot of times you'll see things are inversely proportional. So if A was inversely proportional to B, then that would mean that A would be equal to some constant times 1 over B. And the beginning differential equations we write oftentimes have some type of assumption about the way in which something grows as proportional to the amount of that thing that's present. So one model we're going to be looking a lot at is population growth. And one of the earliest attempts at this was by Malthus. His idea was basically that the rate at which a population of a country grows is proportional to the total population of the country at that time. And that makes sense, right? The more people you have, the more opportunity you have for that population to grow to make even more people. So we would say that the rate of change of the population with respect to time is proportional to the size of the population at that time. In terms of the differential equation, that would give us the differential equation. dp dt is equal to a constant times the population p. Similarly, if we were to look at radioactive decay, the rate at which a substance decays is proportional to the amount of that substance at a particular time. So the rate of decay of an amount of an atom, for example, with respect to time, is going to be proportional to how much we have times some constant of proportionality k. Obviously, if k is less than 0, then this population would be decreasing because it would have a negative rate, so that would actually be decay. If k was greater than 0, then this would be a positive rate of change, and then we would actually expect the quantity to be increasing at that time. For radioactive decay, things like half-life, we would have a negative k value. This could also, for example, monitor the amount of drugs in someone's system at a particular point in time t. If you wanted to know, like, let's say how much aspirin would be in your body 2 hours after you've taken the drug, then you could use a differential equation very similar to this to model the amount of concentration in your bloodstream at a particular point in time. The next model we'll look at is going to be Newton's law of cooling or warming. Suppose that T of t represents the temperature of a body at time t. T sub m is the temperature of the surrounding medium. So T sub m is kind of like the ambient temperature in which the thing is housed in, if you will. the rate of change of the temperature with respect to time is the rate at which the temperature of the body changes. And what Newton's law of cooling says is that the rate of change of the temperature with respect to time is proportional to the difference of the temperature of the item minus the temperature of the medium. Okay. So dt is going to be equal to a constant k times the temperature function minus the temperature of the medium. One that you're definitely going to see in the homework is the spread of disease. Kind of fitting, I guess, with the COVID-19 scenario we have going on right now. But whether it's the flu or COVID or whatever, let's let x of t be the number of people who have contracted the disease, and we're going to let y of t be the number of people who have not yet been exposed. So in this differential equation we're about to write down, the actual function of interest is x of t. We want to know how many people actually have this disease, and how is that rate of those people going to change with respect to time. So x of t is the number of people that have the disease, y of t is the number of people that do not yet have it. And the assumption we make under this model is we assume that the rate dx dt at which the disease spreads is proportional to the number of encounters or interactions between these two groups of people. If we assume that the number of interactions is jointly proportional to both x of t and y of t, then that means that it's going to be some constant times the product of those two. So we would say that the rate of change of the number infected with respect to time is going to be a constant k times the number of people infected times the number of people that are not yet infected. Generally speaking, we would like to get this down to a function of a single variable. For instance, let's suppose we have a community that we're modeling, and let's suppose that that community has a fixed population of size n. So we have this population, they're their own kind of little enclave, if you will, they're their own individual subset, and let's suppose that one person comes into this community that's infected by this disease. Well, we had the n people from before, and now we have this one additional person, so now we have a total of n plus 1 people. We can argue that the number of people that are not infected plus the number of people, the number of people that are infected plus the number of people that are not infected is going to be equal to the total amount, which is n plus 1. This relationship gives us an equation where we can solve for y, just take the x to the other side, and we would get that y equals n plus 1 minus x. And so we can rewrite this differential equation. Everywhere we see a y, just replace the expression for x, and we get that the rate of change of those infected with respect to time is a constant times x times n plus 1 minus x. And then of course the obvious initial condition here would be we started with just one person that was sick initially, so the number of people infected at time 0, which is x of 0, would be equal to 1. We won't focus so much on the chemical reactions. If you're interested, I can do a couple of these during office hours. Another one we will do, though, that's very popular is mixture problems. The mixing of two salt solutions of different concentrations gives rise to a first-order ODE. For example, let's suppose that we have a large tank that initially contains 300 gallons of brine. That's just a saltwater solution. So we have water with a certain amount of salt that's dissolved in it. And let's suppose that we're going to pump another brine solution into the large tank at a rate of 3 gallons per minute. The concentration of the salt in this inflow is about 2 pounds per gallon. And then when the salt is in the tank is mixed and stirred well, it is going to be pumped out at the same rate as when it enters the solution. So we have this tank that already has 300 gallons in it with a certain concentration of brine. We pump some stuff in, we stir it up, and then we're going to pump it out at the same rate. What we want to keep track of is we want to model the amount of salt in the tank at time t. So what is the rate of change of the amount of salt with respect to time? Well, we have some salt that's being pumped in, so it's going to be our input rate, but then we're also pumping some out of this tank, so we have to subtract the rate of output, and so the rate of change of the overall salt concentration is simply going to be the rate in minus the rate out. Let's talk about the rate in for a moment. So one of the things that we know is that the solution itself is being pumped in at 3 gallons per minute. And this inflow has 2 pounds per gallon. So we can convert this rate to figure out how many pounds per minute we're actually going to get. It's 2 pounds per gallon is how much is coming in. And it's coming in at the rate of 3 gallons per minute. So if we multiply that, we'd see that the amount of salt concentration that's entering the tank is going to be at 6 pounds per minute. Now, what about the rate out? So the concentration of salt that's going to be in the outflow in terms of pounds per gallon, well, we have an unknown concentration at time t. So the amount of stuff that's being taken out of the tank is going to be at A of t divided by 300. That'll give us our pounds per gallon. Right, because we have this many pounds, this many gallons. We know it's being pumped out at the same rate it was coming in. That's at 3 gallons per minute. So again, if you multiply this, it'll be 3 A of t over 300, which would give us A of t over 100 pounds per minute would be the rate out of the tank. So if we just kind of put this together, what we have is that the rate of change of the amount of salt in the tank with respect to time is going to be 6 minus A over 100. That is, it's rate in minus rate out. If we wanted to write it in standard form, you'd have the ADT, bring the A term to the left side, and then take the constant term to the other side. So this differential equation is what would model the amount or the concentration of salt in the tank at time t.